one we call it as a contention window and one more we call it as a contention free window. So what you mean by contention window is that in contention window, let's say your MAC layer, if it is working in contention window means, then whatever the nodes wants to transmit the data, they will contain for the channel to access. So means they will fight with the other station to access the channel. So those who wins the contention, so they will get a priority to access the network. Just wait a minute. Those who contain for the, sorry for the disturbance. So in the contention services, the MAC layer will work for the, it means in the form of contention, in the case of contention services, what the stations will do this, they will contain for the channel access. So if the data has to be transmitted over the network means, so directly they will not transmit. First they need to access the channel. So in order to access the channel to data transmission, they should fight with the other station. So how they should fight? They should obey some protocols. So or they should obey some rules. So if the one who obey all the rules and the one who get the chance to access the channel, so that will be permitted to data transmission. So in order to do these services, the MAC layer has created one protocol or one function, we are going to call it as, that function we call it as a distributed coordination function. Is that clear what you mean by distributed coordination function? So in the distributed coordination function, the station will contain for the channel. So the one who gets the station or the one who gets the channel, they will ready to transfer the data. So how they will get the data and what is the procedure they need to adopt to get the data, so that will be governed or that will be explained through the use of this distributed coordination function. There is one more, we call it as a contention free services. So in the contention free services, if the MAC layer is working in contention free services means what? The station will not fight for the channel to access. So what they will do, what in this contention free services the MAC layer will does is, the MAC layer will send a polling signals to the stations. So the station who wants to transmit the data, they will respond to the polling signal for the MAC layer which has been sent. So based upon the acknowledgement which has been received from the different station, the access will be given to the corresponding station so that the station can transmit the data. So this is the main mechanism what the MAC layer will work in a wireless LAN. So in the case of wireless LAN, the MAC layer will work in a two period or two window. So the first window we call it as a contention free window and the one more window we call it as a contention window. And this contention free window and the contention window, they will be switch overing within the network depending upon the availability of node, depending upon the type of the network and depending upon the what type of data we are transmitting and how frequently the data are transmitted over the network. So based upon that, this window size will be fixed. Whereas contention free means the MAC layer will only allocate the station to transmit the data. So the station who wants to transmit the data, they should receive the polling signal from the MAC layer. So once they receive the polling signal and a specific amount of time will be given for each station to transmit, so the station will go for transmission of the data. So in the last class we studied how this distributed coordination function will work. So the distributed coordination function works based upon the CSMA CA technology. So in order to understand the mechanism how this distributed coordination function works, so we have considered 4 stations. So in these 4 stations, let's say that 2 stations are transmitting the data. So the first station we call it as a source and the second station we call it as a destination. Along with that there are 2 more stations, that is a station C and station Z. So when you can see here, when the station A senses the channel, if the channel is free means, so then directly it will not transmit the packet, it will wait for some amount of time. So what is that amount of time? We call it as a distributed interframe space. Once again I am telling you, distributed interframe space. So after that interval of time, it will send an RTS packet. So what do you mean by RTS packet? Request to send. So all these terminologies in the last class only I have explained. And then destination, that is a receiver, what it does is after receiving the RTS packet, it will wait for one more short period of time, and that short period of time we call it as a short interframe space. We call it as a short interframe space. So after that short interframe space elapsed, the destination will send one more packet to the receiver saying that I am ready to send. So what is that? CTS. CTS is nothing but clear to send. So once the source receives and clear to send message, so it will ready and it will wait for some more amount of time, and that amount of time we call it as a SIFS, that is nothing but short interframe. So with the use of once the short interframe space elapsed, the data will be transmitted. So once the data is transmitted or once it is received at the destination, it will wait for again SIFS time. After that, it will acknowledge it. So this is how the data will be transmitted in the distributed coordination function. See, once again I am emphasizing you. So in this wireless LAN technology, this DCF and PCF are very important topic. So any one topic will be appearing for your internals and also for the main examination. Okay, I request everyone, so please attentive and try to learn the concepts. So this is, you understood, right? Distributed coordination function. Okay, so this is the explanation what I have given for the previous slide. Okay, so here, so what it does is, so in order to see the ongoing transmission of the data transmission between the neighboring node, so it uses one of the vector called as a network allocation vector. So through the use of this network allocation vector, so the neighboring node will get to know that what is the transmission time that is undergoing currently. So they will wait for that amount of time, and then again after that amount of time they will try to access the channel. If the channel is free, means again they will go for the DCIFS. If the channel is free, means again they will go for RTS packet, and then they will receive a CTS packet, and then the data will be transmitted. So if this, so what we can do is we can avoid the collision, so by using a handshaking message. So we are using a two handshaking message, that is nothing but RTS and CTS. So through the use of this RTS and CTS, we can avoid the collision during the data transmission. Okay, so this is what all about your DCF frame. The next one, what we call it as a PCF frame. Okay, so this PCF frame we call it as a, or it works based upon the methodology called as a polling. I think polling packet. So the station which will receive the polling packet, they will get an access, or they will get a chance to access the network. Okay, so that is the main method what we are going to use in a point coordination function. So you can see here, it is a contention period. So you can see here, here we have two period. One is a contention free period and one more is a contention period. So in the contention free period, so you can see here the PCIF, that is a polled station, and you can see you have an access point. So this access point will have a provision to send the polling signals. So you can see here, once the contention period is started, so it's wait for a PIFS, that is a polling interframe space time, and after that, so you can see here it has taken the station B and it has sent an polled message to station B. So after that, what happens is, so the polled the station B, it will send and one more signal, or it will wait for the amount of time, that is a SIFS time, that is a short interframe space time. It will wait, and then the access point will transmit this polling message. So once the polled message has been reached to the station, it will acknowledge it and it will transmit the data. It will acknowledge it and it will transmit the data. So once the data has been transmitted successfully, now what happens is, you can see here the AP will get an acknowledgement for the polled message. So the other stations, what they will do is, the other station, they will go for an blocking state. The other station, they will go for the blocking state. That is nothing but they will incorporate the nav, that is a network allocation vector, saying that one already station, the station B is already polled, so the other station, there is no need for them to access for the channel, so they will be not getting any carrier. So therefore what they will do is, so the transmission duration of amount of time for the station B, whatever it is required, right? So that's information will be included, or it will be updated in the network allocation vector. So in the network allocation vector, the station will see that, okay, so this is the time duration with I will not get access to the channel, so there it's better to go for the sleep mode. So you can see, once the station B, it has been polled, unless and until, that is the contention free period ended, the other station they will not get access to data transmission. So when one more free access, that is one more contention free period that has been started, then again other station will be pulled, and if they are having the data means, then they will access the channel. Okay, and you can see this is a repetitive interval. So in the first interval you have a contention free period, and in the one more interval you have a contention period. So in the contention period what happens is, again all station content for the access station, and depending upon the who is going to get a priority to data transmission, so that data or that station will transmit the data. The remaining station, again they will update the network allocation vector, and based upon the data transmission or the duration of time which is needed for each station to data transmit, so after that they will access the channel. So if it is free means they will get the channel, otherwise again they need to contend for the rest of the channel. Okay, so I request all the students kindly make a note of this diagram. This is very important diagram. Please make a note of this. So here B is nothing but it is a beacon frame. So the access point, it will generate a beacon frame, and it will wait for the beacon frame to be elapsed. Once the beacon frame has been elapsed, it will poll a signal to the station. So the station who gets the polling message, no, so they will have a provision to data transmission. Okay, so why it is necessary for us to have a fragmentation is that so when the datagram if the size of the datagram, whatever the packet it has been reached in the network layer, if the size of the datagram it is very large than the transmission capacity of that station or of that device, then we should go for the fragmentation. Okay, so why? Because the whatever the application layer, so the application is independent of the devices. The application layer is independent of the devices. So whatever the data has been generated in the transport layer, it is independent of the frame which has been generated in the network layer. So therefore, in order to match the maximum transmission unit of the data link layer, or sorry, the network layer, we go for the fragmentation. Okay, so what we do it in the network layer is, so the data means the data whatever we are going to receive from the transport layer, it will be divided into a smaller blocks, and each blocks we call it as a datagram. Okay, so from this datagram, so what we can do is, so we can, if the size of the data frame which has been received from the transport layer, if it is large means, then we divide them into smaller blocks, and these blocks or this process we call it as a fragmentation. Then what are the important advantages, or what are the advantages we can have from this fragmentation, you can ask. So the advantages from this fragmentation is, so we can avoid the retransmission of the longer data. So why? Because so if you, let's say you have some 3 MB of data, and this 3 MB of data directly have transmitted. So because in the network or within the network, so the maximum data transmission unit or the capacity of that device, if it is less means, so whatever the data you have transmitted 3 MB of data, that will be lost. So again what you are supposed to do is, again 3 MB of data has to be transmitted within the network. So instead of that, what we can do is, we will see the capacity of the network, so through the use of maximum transmission unit. So from that we get to know that what is the maximum capacity of the channel it is feasible for the data transmission. So depending upon that we can do the modifications for the framing. Okay, so we can do the modifications for the fragmentation, so that we can transmit the successful from source to destination. So means what, we can avoid the retransmission of the longer frame, and we can avoid the corruptions, or we can avoid the collision within the networks also. Okay, so and we can avoid the error correction mechanisms also. Why? Because so if you transmit larger frame or larger size of the frame within the network means, so if anywhere if error has been occurred within the frame means, then the whole frame has to be retransmitted, or the whole frame has to be rejected. So if the size of the frame is very small means, then only that frame or that only that segment can be eliminated and that segment can be retransmitted, whereas the rest of the segments we can join it once again through the use of flow control so that it can be reached to the destination as quick as possible. So therefore we go for this fragmentation method. Okay, so there are different types of framing, that is doing the fragmentation or creation of the frame. So how it has been divided or how we can do the fragmentation will be done through the use of frame format. Okay, so the frame format to do the fragmentation, it contains the following information. So the first it contains a 9 field. So the fragmentation format, it contains a 9 field. So what is the 9 field is? The first one we call it as a frame control. Okay, so what is this frame control? So this frame control, it is of 2 bytes information. So what it does, it defines the type of the frame and control information. So it defines the type of the frame, so what frame we are transmitting, and the controlling information, so how we can do the framing or how we can control this flow of transmission of this frame. So all those information, it will be held in a control frame. So it has a 11 subframes. So it has a 11 subframes. So what are those? It has been given in the second case. So second one is we have a D. So what do you mean by D? D is nothing but a 2 bytes. So what information it holds is, it holds the duration of transmission which has been set for the nav vector. So I told you, right? So in the DCF or in the PCF, when any one station start transmitting means, then the rest of the station, they should activate the nav, that is a network allocation vector. So in the network allocation vector, we will set a time duration. So up to that time duration, the station will not go for the contention of the channel. So that information will be done from the D segment. The next one is addresses. Okay, so the 4 addresses fields of each of 6 bytes. So it contains a 4 addresses field which is of 6 bytes. Okay, so the next one is sequence control. So the sequence control is of 2 bytes. So the first 4 bits defines the fragment number and the last 12 bits numbers gives the sequence number. Okay, so in the fragmentation, so we have done the fragmentation, right? So for each fragmentation, so we will be giving the sequence number and the fragmentation number. So to among this 4 byte, the first 4 bits will be defined for the fragmentation number and the remaining 12 bytes will be given for the sequence number. Okay, so the next one is frame. So frame is nothing but, so whatever the information or whatever the data you want to transmit, no, so we call it as a frame body. So the size of the frame body, which will vary from 0 to 2312 bytes. The next one is we will be using a FCS. So the next one we will be using a FCS. There is a frame control space, so which is of 4 bytes, so which contains a CRC32 error detection sequence. So it contains a CRC32 error detection sequence. So we know that, right? CRC is nothing but, it is a cyclic redundancy check. So this cyclic redundancy check will be have in this FSC frame format. Okay, so this is the frame format of the fragmentation process. So you can see here we have a FC, D, address 1, address 2, address 3, and then we have a SC, address 4, frame body, and followed by the FSC. And I told you this FC, it is having a 11 subfields. So that is nothing but protocol version, type, subtype, and to DS, from DS, that is a destination from source address, and more fragmentation if it is required, and whether the data frame has to be retransmitted, what is the power needed to do the data transmission. Okay, and more data, WUP, and reservation phase, whether it has been reserved or not. So all those information will be included in the FC frame.